Alright, we are recording. So, acid-base titrations. We were looking at these titration graphs yesterday. If we look at this one, we're on the next to last page. What type of acid do we have?
We have a strong acid.
No, what? Oh, that's a weak acid.
Weak acid.
Or we have a weak acid.
What kind of base?
Strong.
Strong base. Alright. Can we figure out Ka from this?
Yes.
Yes, it says, this one actually makes your life easy because it says the half equivalence point, the pH equals pKa equals 4.75. So what is Ka? 10 to the negative 4.75.
So it's always going to be the opposite of it, like.
It's the inverse log.
Okay.
Is what you're doing. So when you put it into your calculator, you go second log, and then negative 4.75, and it should work. I think it's second log. Yeah, it'll give you 10 to the, and then you just do negative 4.75 and hit equal, and it's going to give you that the Ka is equal to 1.8 times 10 to the negative fifth.
So, like, one test, do we have to use, like, the scientific side of the calculator, or?
Yes. Yeah, to do your logs, you would. All right, this is this is weak acid, strong base. It actually tells you that, weak acid, strong base titration curve. This one, if you actually saw the real picture, it's colored. So it tells you that here's phenolphthalein, which is an indicator. It's telling you the pH at the equivalence point is 8.8. It tells you your pKa is 4.89. So we could figure out Ka if we wanted to. And the way, if it ever asks you on a test, hey Kevin, put your phone up. If it asked you to, what indicator would you use with this acid, you would try to match the Ka of the indicator to the Ka of the acid. Okay, so that it's a Ka, it's both Kas, because indicators are actually weak acids. So if they have the same Ka or very close to the same Ka, then they're going to work correctly. Or it's going to give it to you as a pH range, that the indicator works in this pH range. So then you would need to find an acid that's in that pH range. So that's what you would do. All right, so down at the bottom you have another one. What kind of acid? Weak. What kind of base? Strong. Equivalence point is right here. And we could figure out, okay, the half equivalence point is right here. Carry it across. The pH is a little bit below 4, so I would say maybe the pH is equal to about maybe 3.9. Is that what y'all would say? Which would equal our pKa. So our Ka is equal to 10 to the negative 3.9. So you do second log negative 3.9, and I would get 1.3 times 10 to the negative fourth.
Like, would it be like that different if we just got 4 instead of 3.9?
No,
So
not really.
It doesn't have to be like dead on.
Mm-mm.
As long as it's close, right?
Right. Well, and especially if it was a multiple choice question, then, you know, they would have all of the choices far enough apart that if you knew what you were doing, it wouldn't be anything around that.
Okay.
Like, if it asked you for the Kas, then if it was given the Kas, it would be like 10 to the negative fourth would be one answer choice, and then another one would be like 10 to the negative 6, 10 to the negative second, 10 to the negative 10. So
The closest one.
Yeah.
I
So
mean,
it would be-
shouldn't be that hard, is what you're saying.
Right. So, because, you know, on the multiple choice, you don't have a calculator. So you're going to have to be able to do easy math. Okay. This graph. Does it look different than what we've looked at?
It looks weird.
What is that?
All right. Do you see, this looks like one curve right here. And then this looks like another curve. So, if you have two curves, what kind of acid are we dealing with?
Like a hella strong.
Not appropriate. But no, it doesn't have anything to do with the strength. Do you remember us talking about diprotic and polyprotic acids? Okay. What is the difference between a regular acid and a diprotic or a polyprotic? What do the diprotics have more of? Hydrogens. Remember? Okay, so diprotic, if you break the word down, di means two, protic means, sounds like proton. So it has two protons that it can donate, which means it would have to have two hydrogens. Can you think of a strong acid that has two hydrogens? H2SO4 is a good example of a diprotic acid. So that means that it dissociates twice. Remember us talking about it, you had the first dissociation. So you would have the acid like H2SO4. Right, in water, the HOH is going to break down. And H plus is going to come away. Okay? That hydrogen gives up a H plus, and you're going to wind up with HSO4 minus. Remember that? Okay?
But if it gave away two hydrogens.
Well, okay, so it's giving away one, the first step. The next step is you're going to take the HSO4 minus, you're going to dissociate it, and it's going to have, the next H plus is going to come off, and you've got SO4 2 minus left over. When it gives away that other H. Remember that?
Can it keep giving away H's? Just like.
Well, I mean, at this point, it has no more H's to give away. It's an SO4 2 minus ion. There's no more hydrogens. It's completely dissociated. And remember, we talked about the Ka of the first dissociation is lower. The Ka of the second dissociation is going to be a lot higher. It's going to take a lot more energy to remove that second proton away. All right, so you really have two curves going on here. This is the first proton removal, this first part. This is the second one. So that means you're going to have two pKa's. So if we, if this is the equivalence point, then the half equivalence point would be somewhere around there. So the pKa1 is right here. So that's what this says is pKa1. So the first dissociation. The second equivalence point is around here, half equivalence point. So this would be your pKa2. We can't actually calculate it because there's nothing on the pH scale. There's no marks. So we can't say anything much other than just realizing that that's where the pH would be. But now if you look at the next one, this is also a diprotic, right? You got two curves. This actually gives you, it makes your life easy. It gives you your pKa1, 2.34. It gives you your pKa2 of 9.69. So you could take that and calculate your Ka's for your first dissociation and your second dissociation. Just from looking at that graph. All right, this one down here, this is actually a diprotic acid, but this is these are amino acids. So you would see this organic. or biochem. This is actually the amino acid glycine, and that's nothing you have to know, and you wouldn't have to know that on the AP test either. But just know that, well, and it actually tells you glycine there. But just know that you could calculate the Kas from this also. It wouldn't matter that it's an organic molecule instead of inorganic. You would just, it gave you the pKa's of each one, so you would just use them. And it actually is almost identical to this one up here.
So if they give you the pKa's, you don't have to do anything. You just use them.
Well, you would then have to calculate Ka, you would have to, like pKa of 2.34, then your Ka would be 10 to the negative 2.34, so you'd have to calculate it.
And you just do that by putting a log in.
Inverse log. So on your calculator, you put second log, you push the second button, and then hit log.
But wouldn't you put a negative in front of it?
And then you would say,
Negative.
you would put, for the exponent, you would put it as negative. Yeah.
I didn't know that. I put a negative.
All right. Now, if you're calculating pH, it is the negative log. You do negative log.
Oh, so you don't have to do negative log.
Now, your negative is there for the exponent this time. All right, now look at this one. It's got 3. So what do we call an acid that has more than 2 hydrogens? Polyprotic. So this is a polyprotic. And so you could go through and your half equivalence point would be there. So this would be pKa1, and then half equivalence point would be here. This would be pKa2, and then pKa3. If there were numbers on the pH scale for us to read. But there's not numbers, so... they wouldn't actually ask you for anything on that. They might, on this, you see how it's labeled like A, B, C, D, E, F, G? They might ask you what those mean. So like this would be the equivalent point for the first association. This would be the half, this B point would be the half equivalent point. That would be, A would be the pH or the pKa of 1. So they would ask you just to tell them what that is. Questions? All right. Now I have something else for you. I know you're excited. We are going to do some practice multiple choice. We are going to do it together. We're not going to sing Kumbaya on this.
Hey, Moni, get on your own head. You can't tell me stuff.
All right. So look at number 1. The pH of a 0.1 molar. Okay, now remember, this is multiple choice. Multiple choice means easy math because you don't have a calculator. So you've got to not overthink these things, which is a problem that a lot of you have. All right, we have pH of a 0.1 molar sodium hydroxide. Sodium hydroxide, strong or weak base? Strong. Strong base, think of your titration curves. What number of pH is a strong base near? Way up near 14, right?
My bad. I thought we were talking about
Way up near 14. Base, remember, is up at the top.
Yeah.
So which one of those is closest to 14? 13. Don't overthink. It really, some questions really are that easy, y'all. All right, number 2. This one requires a little bit more thinking. Which of the following reactions does not produce or proceed significantly to the right? so that means you got to look at. Oops.
Oh.
We can write on
Computer.
this, Rob.
Yes, this is yours.
Okay.
All right. If you take HCN and you add OH to it, are you going to get water and CN minus?
I mean,
Does
yeah.
it proceed that direction?
I mean,
If you take that H and you put it on the OH, does it become HOH, which is water?
yes.
Yes. And then what you have left over is just CN minus.
Yes.
So yes, this goes to the right. All right. CuH2O4 plus 4 ammonias. Do you get? Will you get CuNH3 4 plus 4 waters? Does it go that way? Double replacement, or actually, it's a single replacement. Yeah, it will. H2SO4. Will it dissociate in water to H3O plus and HSO4 minus? Yes, it will.
Yeah.
That's how acids dissociate. We just talked about that. Loses a hydrogen, becomes HSO4 minus in the first dissociation. All right, so let's look at this. Can you take water and add it to an HSO4 minus ion and get sulfuric acid?
Nope. Nope.
No. That should be going that direction. So your answer is that one. All right. All of the following species can function as Bronsted-Lowry bases in solution except, okay, what is the definition of a Bronsted-Lowry base? What does it do? Does it gain or lose protons? Does it accept or give away? Accepts protons. Accepts protons. All right, can you add a proton to water and get something? What do you get? H3O plus. That's legal, right? If we add an H plus to ammonia, do we get something that's legal? And H4 plus, is that a legal thing? Ammonium ion, right?
Yeah.
If we add an H plus to NH4, have you ever seen an NH5 2 plus?
That's illegal.
That is not right. It's that one. I have never seen an NH5 either. So there you go. All right. Remember us talking about conjugate acids, conjugate bases. You got to know what the acid is, what the base is, what its conjugate acid, conjugate base is. So you need to be able to identify these. If you do not, you need to look on the first 2 pages of your notes and reread those. So H2PO4. Does that sound a lot like H2SO4?
Yes.
Would that be an acid? Yes. So don't overthink it. If that's an acid, what does this have to be? A base. So what would be the conjugate acid for this H2PO4? It has to be, the conjugate base, I'm sorry. You've got an acid, what is its conjugate base? That, right? When it loses, wait, I did that wrong.
Yeah, that's what I was thinking.
Sorry, conjugate base. Sorry, didn't mean to confuse you.
Yeah.
I was looking up there and writing down here, and that's not a good combination. So if this is my base, then this is my conjugate acid, right? Okay. So now that I know that, which one are my acids and which ones are my bases?
A.
It is A. Acids are this one and this one. And bases are this one and that one. And that's A. All right. Number 5. Commercial vinegar was titrated with sodium hydroxide to determine the content of the acetic acid HC2H3O2. For 20 milliliters of the vinegar, 32 milliliters of 0.5 molar sodium hydroxide solution was required. What was the concentration of acetic acid in the vinegar if no other acid was present? Okay. Lot of words.
Break it down.
There is a formula that we've not talked about until this point, but it's super easy. Do y'all remember the dilution formula?
Yeah.
M1D1 equals M2V2?
Yeah.
You can use the same thing except say MAVA is equal to MBVB. A means acid, B means base. Okay? So the molarity and volume of the acid is equal to the molarity and the volume of the base. Now, does that make sense when you talk about the equivalent point, where we talked about the moles of acid equals the moles of base at the equivalent point? Okay. So, if we substitute in, well, and actually we need to solve for, we're looking for the concentration. So, we're doing MA is equal to MBVB over VA. Substitute in, MB is 0.5, VB is 32, VA is 20. All right, you don't have a calculator, so let's think about this. What is half of 32? 16, because 0.5 times 32 is half of 32, so we got 16 over 20. If I reduce that, if you look at all of these are all, like, most of them are tenths, right? So if I just reduce it to 8/10, which one is 8/10? B. Easy math. Don't overcomplicate. Number 6, what is the pH of a 1 times 10 to the negative second molar solution of HCN? And then it says for HCN, Ka is equal to 4 times 10 to the negative 10. All right. Weak acid. HCN is a weak acid, correct? If it is a weak acid, its pH has to be below 7, right?
So it's not A, B, or C.
So, if it is below 7,
Wait, was it a strong acid or
it's a weak acid.
weak acid?
It has to be D, right?
Yeah.
All the others are bases.
Or neutral.
Was that one hard? No. I mean, you could have gone through the long process of figuring it out. But why, when you can reason? Okay? Think. 7. In liquid ammonia, the reaction represented above occurs. All right. Ammonia, is that an acid or a base?
It's usually base.
It's a base. All right. So if that's the base, bases accept protons, right? What's its conjugate acid when it accepts another proton? It's that one, right?
Yeah.
Okay.
You're right.
So, what is the answer? It says in the reaction, NH4 plus acts as C, the conjugate acid of ammonia. Number 8, which of the following solutions has a pH greater than 7? All right, you've got to look at these. I'm looking, this one is acetic acid. If it's an acid, its pH is going to be less than 7, right? And that one's not it. So now these others are all salts. So remember, for a salt, you have to look at what the acid and the base are that make it. Okay, the first part is going to be the base. So KOH, is that going to be a strong or a weak base? K is in the first column, so this is a strong base. Br, HBr is a strong acid. Strong, so it's neutral, right?
Yeah.
So that's neutral, so that's not it. Ammonium hydroxide, NH4OH. That's a weak, right?
Yeah.
Weak base. HCl would be a strong acid, strong wind, so it's not that one. So process of elimination, it has to be that one. But if you figured that out, NaOH is a strong base. and HF is a weak acid, strong wind, so that one would be a basic salt. So it would have a pH greater than 7.
This is actually pretty easy.
So far, yeah.
Okay, then that means it's going to get harder.
As water is heated, its pH decreases. pH is going down. So it's asking why.
The water's no longer.
All right. Well, do you think that's really a good?
Come on.
Is that really a good explanation?
I'm just making fun of it.
Well, I know. I mean, technically it is right, but is that really the? You get into what's the best answer.
Let's see.
All right. The KW is decreasing.
Oh, because it's like Ka times Kb, so.
Right, and so that's not it. The water has a lower hydroxide concentration than cooler water.
That
Sounds reasonable.
Maybe. Okay, then look at D. The dissociation of water is an endothermic process.
That's
Endothermic means it has to take in heat to be able to. Okay, so think about dissociation. You got water breaking up into H plus and OH minus. Is that going to do that by itself? Or is it going to take energy to break that water molecule apart? It's going to take energy. And if you're heating it, is it taking in energy to be heated? Yes. And that's the endothermic process, right? So, D. 10. You have 100 milliliters of a solution of hydrochloric acid, strong acid, right? pH of 3. You add 100 milliliters of water to the solution. What is the resulting pH of the solution? All right, first question is, if you are adding water to the solution, are we diluting it? Yes. And remember how water can act as an acid or a base? Okay, so keep that in mind. So if we're diluting it, it's actually being diluted by a factor of 2, right? So you're adding, you had 100, now you're adding another 100, or you had 100, adding 100, that makes 200, right? So we doubled the volume. So if we doubled the volume, then the pH has to be greater than 3 because we've doubled that volume.
Well, then all of our answers
So
C says that.
the answer is D. None of the above is correct, but the pH must be greater than 3.
But all the other ones are greater than
No, C is pH is equal to 3.
Well, I canceled out
A and B are greater than, I mean, it shows greater than 5, but you don't take the average of 3 and 7, and you don't add the pHs together.
I didn't think I did.
So neither one of those work. You can work it out in a long problem, but there's no reason to. You just got to think about it. Okay. 11. 25 milliliters of sodium hydroxide. Is that strong or weak? Strong base, right? Mixed with sulfuric acid. Strong acid. Okay? So, if they're both strong, are they going to completely dissociate in the water? What's the definition of strong?
They don't break up. Oh wait, they break up.
They break up. Okay, remember strong means weak bonds. So they completely dissociate in the water. So at the equivalence point, okay, when it had, or at the end point, when everything has reacted, are you going to have any of the beginning things left? Am I going to have any base or any acid left? No. What you're going to have, you got to think about what the reaction would be like. It would be like NaOH plus that H2SO4 is going to dissociate. You're going to wind up with sodium sulfate and water. So the answer is B. All that we will have left in the beaker besides the indicator is the sodium sulfate and the water. Now, if it were weak, would we have some of the beginning base or acid left at the end? Yes. Okay, so that's what you got to remember. Weak acids or weak bases do not completely dissociate. So at the end point, you're still going to have some of that original acid or base, or both, if they're both weak. All right, in titrating 0.2 molar hydrochloric acid with 0.2 molar sodium hydroxide, the solution at the equivalence point is what? Okay, so this is one you got to think about too. At the equivalence point, our concentration of our base is equal to our concentration of our acid. So volumes have to be equivalent. All right? So if they have the same volume and you're adding 0.2 molar volume of hydrochloric acid, 0.2 molar volume of sodium hydroxide, volume plus volume is twice the volume, right? So if we have 0.2 divided by twice the whatever that volume is, what's 0.2 divided by 2? 0.1. Because remember, it's moles per volume, whether that's liter or it's really moles per liter is what molarity is. All right, this one is not difficult. Assuming an indicator works best when the equivalence point of a titration comes in the middle of the indicator range. Which of the following titrations would methyl red be the best indicator? All right, methyl red, we need a pH between 4.8 and 6. Okay, methyl red, we want to look at this. All right? So this is where we cheat and just look at those exponents. So we're not even going to worry about A right now. Look at the exponents of B, C, and D. 10, 5, and 6. Oh, I'm sorry, 10, 5, and 4.
Wouldn't it be D? 4? No, it would be 5.
Yeah, so C.
And C.
Is it really like that?
Mm-hmm.
That's
Seriously?
I told you it's not that hard sometimes. Y'all just make it difficult. 14, in deciding which of the two acids is the stronger. What is it that we always look at for the acid? What it's these K values. What are the K values? What's Ka? What does Ka actually stand for? It's the equilibrium constant.
So C.
$15. You have 100 milliliters of each of these acids. And it says rank the pHs of each of the solutions from highest to lowest pH. Again, all you need to look at is those exponents.
would be like what?
Highest to lowest. Which one would have the highest pH?
Oh, HCN.
HCN.
Which is
And the only one that starts with HCN is the first one.
can't be D because you won't know that.
Because the smaller the Ka, the weaker the acid. Weakest acid is going to have a higher pH. That's all you really got to look at.
So the weaker the acid, the higher the
Yeah,
Mhm.
because the more it takes to break it down.
Mhm.
Because it won't break down.
All right, 16. For the equilibrium that exists,
I have a question for NHS hours. I translated papers into English to Spanish. Does that count?
was it for a family member?
No.
As long as it wasn't for a family member and you get them to sign, that's fine.
Okay. Thank you.
Equilibrium. K is equal to concentration of the products over the concentration of the reactants, right? we're doing the dissociation of HNO2. So HNO2 is going to break down H plus and NO2 minus. Product over reactant. Which one has that?
H plus NO2?
H plus times NO2 over HNO2.
Why is it time?
Why is it
Because
time?
it's the products over the reactants.
Oh.
No.
Y'all been doing this?
I'm saying when you wrote the.
Oh, I didn't put my plus there.
Yeah, I was wondering why.
I see what y'all were talking about.
Oh, okay.
Well, they were roasting you in the seeds.
Just picking me apart. Keeping me on my toes. All right, 17. All right. You've got these Kas of these acids. Remember, the smaller the Ka, the weaker the acid. And remember, if you have a weak acid, what is its conjugate base going to be? Weak or strong? Strong. Because remember, it's opposite. So if you have a strong acid, it's a weak conjugate. If you have a weak acid, it's going to be a strong conjugate. So if we want the strongest conjugate base, then we need the weakest acid, which has the lowest Ka. Which one has the smallest Ka?
Lactic acid.
Smallest, look, this is -5. These are -4.
And then it's propionic acid, so 8.
Propionic acid. Does everybody agree that that's the smallest Ka?
Yeah, because
Okay.
it's 1.3 and the other one's 6.
Because look, okay, if you move this 5 decimal points, that's 0.000013, and this would be 0.000063. Which one's smaller?
Okay, so you
The
said-
1,3, right?
Yes. Yeah. Okay, so what did you say about the weak?
Weak.
conjugate and the strong.
Weak acid is going to have a strong conjugate base.
And then the strong
Not equal, but, and then if it was a strong acid, it would have a weak base for a conjugate. And this is conjugate. Right, and the same thing, if you had a strong base, because it goes both directions, strong base would be a weak acid, conjugate acid, and if you had a weak base, it would have a strong conjugate acid. So they're opposite. All right, rank acetic acid, hydrocyanic acid, and hydrofluoric acid in order of increasing strength. Which one is the strongest? Which would be the one with the highest?
That would be A. For the H.
Wait, no, wait a minute.
She's up.
In order of increasing, so we need the weakest one first. Which one's the weakest? It's A.
What? Huh?
This one is the weakest acid.
But it has.
It has the smallest Ka. Remember, weakest acid has smallest
I thought the smallest
Ka.
exponent was the least.
It's the greatest if it's negative.
It's negative.
Oh yeah.
So it would be largest exponent. But then if it has the same exponent, you got to look at what the numbers in front are. All right, 19. Looks difficult. You got this diagram. Which of the following salts is most likely to form an aqueous solution having the pH shown in the figure above? What pH is that?
7.
Which ones have a pH of 7?
Well,
A neutral one.
KCl is a strong acid, so
No,
that's
even strong.
Strong acid, strong base is going to give you a pH of 7.
So D.
So which one is the strong? It's D. Don't overthink. Which of the following would be the best mole ratio of conjugate acid to conjugate base for a large buffer capacity? Okay, buffer capacity is, in other words, which one would make the best buffer? 1 to 1. Yeah. Why would it be 1 to 1? Because the whole purpose of the buffer is that you got acid and base there to counteract, right? If you had a whole lot more acid than you had the base, are they in balance and going to balance themselves out? No. So you got to have equal amounts. All right. Free response over here.
We have 3 minutes. Come on, Miss Patton.
Well, quickly. And we're not gonna get too far in this one because we're running out of time. But I will post the answer key on this.
Okay.
But look at A. Calculate the value of H plus if it has a pH of 4.95. pH, remember, is negative log of H plus. So can I solve for H plus? Is equal to 10 to the negative pH. So if I get the negative log of that, I am actually, I don't remember what it is, but do 10 to the negative 4.95, and I don't know, you'll get it.
We will have our calculator.
Yes, and free response is not going to be till Monday. Before y'all leave, though, I want you to, or as you leave or whatever, I want y'all to pick up these 2 things. This is just a short little review again about titration calculations and curves. Y'all need to look at it. This is what I actually posted on Google Classroom. It's sample free response questions. The answers to these are on the videos that are attached with that, if you care to look at it to prepare for the test on Monday. So, but there's you a copy of it if you would like to have a copy of the free response questions.
You want to